Hi guys, welcome to your first video. I'm hoping that we can keep these going for as long as we're doing online learning and that it'll be beneficial for you guys. So the first thing I'm going to have you do is pull out a piece of paper and you're going to label it 10.1 to 10.3 U tries. The U try boxes that I usually have on your notes when we take them in class, the little practice problems that you do, those are embedded within this first PowerPoint, and I'm actually going to have you submit those to Canvas as we go. So the only way you'll be able to access the U-Tries is by watching this video. So that's sort of my way of ensuring that you're getting the notes and that you're doing the practice problems. Once you do the practice problems, you'll upload them to the Canvas submission box that says 10.1 to 10.3, and then you'll get credit for watching this video. So you can go ahead and pause, get out a piece of paper, and get ready for that. As soon as you have that, we'll get going. Okay. So we're going to start with 10.2 really. So you already took notes on all of this, so hopefully this will be just a little bit of a reminder for you and clear up anything that may be sort of confusing. So the first thing that we're going to look at here is, let me get a pen going, is Lewis structures. And in order to understand Lewis structures, you really have to understand what valence electrons are. And valence electrons are things that we actually already talked about. We talked about valence electrons when we were doing electron configurations. Remember, electron configurations are these fun guys right here. Now, the valence electron portion of electron configurations is looking at the electrons that are in the outermost principal shell. So that's the shell that has the highest energy and that's furthest away from the nucleus. So looking at this particular electron configuration, we can see that level 2, or n equals 2, is our highest principal shell, or our outermost principal shell. So we're going to look at how many electrons are sitting in the n equals 2 level. And in this case, we have 4 and 2, so we have a total of 6 valence electrons. Now remember, valence electrons are different than the total electron count. The total electron count here is going to be 8. So that's the first thing you have to remember. We can also look at how many valence electrons something has by referencing the periodic table. So remember, each column, especially if we're looking at metals and nonmetals, not transition metals, just metals and nonmetals, we'll be able to determine what the valence electron count is by looking at what column they sit in. So each of the columns has a number associated with it. So if you look at the top of the periodic table, whatever column that particular element is sitting in will tell you how many valence electrons it has. So those are the two ways you can tell. Now the next thing we're going to look at is what Lewis structures are. And Lewis structures are a visual representation of how many valence electrons something has. So the first thing you're actually going to do is draw the chemical symbol for whatever element you want to draw a Lewis structure for. So in this case, we're still looking at oxygen. So I would write an O as my chemical symbol, and then I have 6 valence electrons that I need to distribute. So the way I like to do this is start with 1 on each side. 1, 2, 3, 4, and 5, and 6. So I usually put 1 on each side before I go back and double them up. Now, this would be the Lewis structure for oxygen. Each dot on this structure is representative of 1 valence electron. Okay. So this is going to provide you with sort of a checklist almost of how you fill dots in on your chemical symbols. So again, each dot represents a valence electron. Each side, so if I'm talking about sides here, let's say I'm looking at carbon, this is a side, this is a side, this is a side, and this is a side. There's 4 sides, and each side can hold up to 2 dots on it. Okay, so I can have a total of 8 valence electrons around one chemical symbol. No more than 2 dots on each side. You can choose how you fill each side and where you start. It doesn't matter. You can start here, you can start here. Either place is fine. Just as long as you're not putting more than 2, it doesn't matter. Now, of course, some things will have only 1 valence electron, so things like lithium, there's only going to be 1 dot, and you can decide where you put that dot. Or beryllium, which only has 2 valence electrons. You could have put the dots on the top and the bottom, and that would have been acceptable as well. Okay, so we're at our first U try. So you're going to pause, get that piece of paper, you'll label it U try number 1, and you're going to draw 3 different Lewis structures. So one for boron, nitrogen, and neon. So the first thing that you're going to want to do is identify the valence electron count. Once you identify the valence electron count, then you can draw your Lewis structure. Okay, so go ahead and pause me here, write your diagrams out, and then as we go to the next slide, you'll notice all the answers are there, so you can use that as a check. I'm not really looking to see if you got everything correct. I'm just making sure you're watching the videos and you're at least attempting the problems. So we'll go ahead and move on here. Okay, so here is boron, nitrogen, and neon. So boron has 3 valence electrons, and really for all of these, by the way, I just looked at the periodic table. So boron has 3 valence electrons, and I distributed my 3 dots around my B for the chemical symbol for boron. And again, I could have really put those 3 dots in any order. Nitrogen has 5 valence electrons. Those 5 valence electrons I chose to double up to on the right-hand side. Again, you really could have put them on any side. And then neon is a noble gas. We know noble gases have 8, and they actually have every side filled with every dot. And we'll learn what this is actually called. Okay. That full set of dots around each side of your element is actually called an octet. And an octet means you have 8 valence electrons and each side is completely full. That is the most stable an element can be, having all of these dots filled out. Most elements want to achieve this. They want to achieve this very stable setting. And we're going to look at how elements achieve those 8 dots around them by sharing or donating electrons or transferring electrons. So this is called having an octet, and that's just having 8 valence electrons around your symbol. Now, some elements are happy with just a duet, and a duet basically is just 2 valence electrons. It means it's still very stable. It doesn't need to have its octet. It can't have an octet, but it will still reach the same level of stability having just those 2 valence electrons, and helium is an example of that. Okay, so let's look at different types of chemical bonds. So a chemical bond is either the sharing or transferring of electrons in order to reach some sort of stability. Now, we'll look at 2 different types of chemical bonds, ionic and covalent. So in an ionic bond, you're actually going to be transferring electrons. So in the example that we're using here, we have sodium and we have chlorine. So sodium is actually going to donate its 1 electron to chlorine. As sodium donates or loses 1 electron, it's actually going to become positively charged. And as chlorine gains an electron, it's going to become negatively charged. So now I have a sodium atom with a positive charge, or an ion, and I have a chlorine atom with a negative charge. I also now have a chlorine atom that has 1, 2, 3, 4, 5, 6 electrons around it, which is what you're seeing here. And what's actually going to happen is this sodium is going to bond to this chlorine because they are going to be attracted to each other. Positive is attracted to negative, so it is going to be this electronic charge that keeps them bonded together. That's an ionic bond. In a covalent bond, we're actually going to see the sharing of electrons. So instead of donating, the 2 elements are actually going to come together and they're going to share whatever electrons they have. So in this case, we have 2 hydrogen atoms. They each have 1 electron, and they are going to be joined together, and that's going to create a covalent bond. And we would write this as something like H2, right? Any type of bond that you're looking at, whether it's ionic and covalent, it's important to note that they're coming together to become stable. So each of these, ionic versus or covalent, it doesn't matter. These are both going to lead to stable electron configurations, and that's really what you need to get out of that. Okay, so what's the octet rule? So the octet rule basically says that in chemical bonding, so we just mentioned chemical bonding on that previous slide, atoms transfer or share electrons to obtain outer shells with 8 electrons. So the octet rule basically says we want atoms want, Oh no. It basically says atoms want a full octet because they want to be stable. So the octet rule says that when we transfer or share electrons, we are going to try to reach those 8 electrons, or we're going to try to reach that full octet. Again, we still have ones that are happy as a duet, things like hydrogen and lithium, and that's sort of the exception to this octet rule. Okay, let's look at 10.3, Lewis structures and ionic compounds. So again, let's focus on what ionic means. So in ionic bonding or ionic compounds, it's important to note that that's a metal bonded with a nonmetal. And when a metal is bonded with a nonmetal, the metal is always going to transfer its electrons to the nonmetal. Transfer electrons to the nonmetal. That's kind of what defines an ionic bond. And when we lose an electron, like the metal is going to be losing an electron, it's going to get a positive charge, or it's going to become a cation. So the metal will become a cation, and the nonmetal is going to gain an electron, and it is going to become negative, and it is going to be the anion. And again, the two of those together, those varying charges, the negative and the positive, are going to be what forces those two to be attracted together. That's an ionic compound. Okay, so let's look at an example of how we would bond together something in an ionic bond, or how two elements would be ionically bonded together, and then what the Lewis structure would look like for that, because that's really what we're focusing on this unit. So in this case, I want to bond together potassium, which is a metal, and chlorine, which is a nonmetal. So the first thing I want to do is determine how many valence electrons each of these have. So potassium has 1 valence electron. It has 1 valence electron, and it is a metal. Chlorine is a nonmetal, and you'll see it has 1, 2, 3, 4, 5, 6, 7 valence electrons. Now, because this is a metal and a nonmetal, I can immediately identify this as an ionic bond. And I know that the metal is always going to donate to the nonmetal. So potassium is going to be transferring its 1 electron to chlorine, or its 1 valence electron to chlorine. So what will happen is this 1 electron is going to be donated to chlorine. So what I end up with is just K with no electrons around it, and then I end up with chlorine, which has now 8 electrons around it. It actually has its full octet, so it's actually really happy. Now, this does not mean that potassium does not have an octet. In fact, potassium actually does have an octet and is actually very stable and happy. That octet just exists at a lower principal shell. So it's at a lower principal shell than the chlorines, but it has actually reached its octet just at a lower energy level. Now, the important thing to note here is also how is the format on how we write this. I told you that when an electron is lost, or when this metal loses its electron, that's a positive thing. If you lose an electron, that's a positive thing. You become a cation. So potassium ends up with a positive charge, a 1+ charge. We don't have the 1 written, but you could write a 1+ charge here. Now, chlorine has gained an electron. That's a negative thing. So it ends up with a negative charge. It's also important to note that we always put brackets around the anion. So you put brackets around the chlorine, and then you have a negative symbol up in the right upper hand corner. And again, that's a 1- charge. Now, if we had gained 2 electrons, then this would be a 2- charge, and we'll be looking at this. And again, this ionic bond is held together because positive and negative are attracted to each other. Okay. So we're coming up on our next U-try here. I want you to write the Lewis structure for the compounds MgO and NABr. And both of these are going to form ionic compounds. Or both of these are ionic compounds, so they're going to form ionic bonds. So you are going to be doing exactly what we did on the last slide. So this is where you'll pause. You'll do U-try number 2 on your piece of paper. And as we move to the next slide, it'll have the answers. Okay. So let's look first at MgO. So magnesium, or Mg, is a metal and oxygen is the nonmetal. So my first step is to identify how many valence electrons each of these have. So magnesium has 2 valence electrons and oxygen has 6 valence electrons. So I've gone ahead and drawn my individual Lewis structures for magnesium and oxygen. And I know that in order for this ionic bond to work, magnesium has to then donate 2 valence electrons to oxygen, which works out really well because oxygen is short 2 valence electrons from having its octet. And remember, it wants an octet because it wants to be stable. So magnesium is going to go ahead and take these 2 electrons, these 2 valence electrons, and it's going to donate them to the oxygen. So the oxygen is going to get those 2 valence electrons. Magnesium lost 2 valence electrons, so when it loses 2, that's a positive thing, so it gets a 2+ charge. Oxygen gained 2, so that's a negative thing, so it has a 2- charge, but it now has its full octet, and remember we put brackets around our anion. For NaBr, so we have sodium. Sodium is our metal and bromine is our nonmetal. Sodium has 1 valence electron. Remember, we found valence electrons by looking at the periodic table or completing an electron configuration. And bromine has 7 valence electrons, so it is missing 1 to fulfill its octet. So sodium is going to donate its 1 valence electron to bromine, and bromine is now going to have its full octet. Sodium lost 1 valence electron, so it has a 1+ charge, and bromine gained 1 valence electron, it has a 1- charge. And remember, we put the brackets around bromine. Okay. The next thing we're going to predict is formulas. So formulas, remember, are different than what we've been looking at. Formulas are depicting exact quantities. This is looking at the subscript if we were going to write out this formula. So a formula looks at how a quantity of each of the elements that make up a compound. So if I want to bond together sodium and sulfur, I need to know how much sodium I need relative to sulfur. And I can actually figure this out using a Lewis structure or a Lewis diagram. So I want to combine sodium and sulfur. So I have sodium, which is Na, and the first thing I'm going to do, as always, is figure out how many valence electrons it has. Then I'm going to look at sulfur, same thing, find out how many valence electrons it has. Sodium has 1 and sulfur has 6. In order to gain an octet, sulfur needs 2 valence electrons. It needs to gain 2 electrons. Sodium has to lose 1 electron. So even if sodium donates its 1 electron to my sulfur, sulfur still does not have an octet. This side is still blank, which you see, or it still needs 1 right here. So in order for this to gain another one, I actually need another sodium. I need another sodium with another valence electron. Then this sodium can then donate to sulfur. So you've probably figured this out by now. That means I need 2 sodiums for every 1 sulfur. So I'm still going to write out my Lewis structure in its proper way. You'll note, though, we have 2, so now proper arrangement shows that we'll have a sodium on either side of the sulfur, and you'll see that each is donating 1 electron. Sulfur now has its full octet. But look at this, sodium, each sodium only donated 1 valence electron, so they have a 1+ charge on each side. But sodium received sulfur received a total of 2 valence electrons, so it has an overall 2- charge. So you have to, that's an important notation to look at. So our final answer, because it's asking us to predict formula, is actually Na2S, because we have 2 sodiums to every 1 sulfur. Okay. All right, so you're going to go ahead and do U-try number 3. You are going to predict the formula for each compound using this Lewis structure diagram for first calcium and chlorine, and then magnesium and nitrogen. Okay, so go ahead and do that. You'll pause, work on this, write it on your piece of paper, and this will be our last U-try. Okay, now here are the answers here. So let's look at calcium and chlorine first. So calcium, again, the first thing you're going to do, depict how many valence electrons it has. Calcium has 2 valence electrons. Chlorine has 7 valence electrons. So chlorine, just by looking at this already, only needs 1 more valence electron to fill its octet. But calcium has 2 valence electrons that it can give. So in order for that to work out, we're going to need more than 1 chlorine. So in this case, we're actually going to put our calcium on the inside, and we're going to pair it with 2 chlorines. That way calcium can donate 1 electron to each of our chlorines, and then each chlorine will have a full octet, which you see here, and our calcium will also now have its full octet as well. And again, take note of the charges. So chlorine received 1 valence electron here, so it has a 1 minus charge. Calcium donated 2 of its valence electrons, so it has an overall 2 plus charge. So this would be the correct notation, but again, this question was asking for us to depict formula. So the formula and the actual final answer here is CaCl2. Now magnesium and nitrogen may have been a little bit more of a challenge for you. Magnesium had 2 valence electrons and nitrogen had 5 valence electrons. So this one actually was probably the most challenging one we've seen yet. You actually needed, in order to get everything all balanced out together, you needed 3 magnesiums. So each magnesium had 2 to give. So even if we donated these 2 magnesiums here and here to this nitrogen, the nitrogen still didn't have a full octet. So we needed an additional magnesium. But our additional magnesium has 2 valence electrons, and nitrogen only had room for 1 more right here. So we had to find another place to put this one. So we needed another nitrogen, and that required us to get a 3rd magnesium. So if we were to write this full Lewis structure out, it would look like this. Again, taking note of charges. Nitrogens each gained 3 valence electrons here, so they had a 3 minus charge, and each magnesium donated 2, so they had 2 plus charges. And we had 3 magnesiums to every 2 nitrogens, so this ended up being our complete formula. Okay, so that's going to be the end of this, this lesson for today. Hopefully you got through all 3 U-tries. You'll take a Genius scan or a picture of what you wrote, and you'll submit it to the Canvas box that says 10.1 to 10.3 notes. After this, there's going to be another video lecture that you're going to look at that's 10.4 to 10.6, and it will have a similar set of questions that you'll be answering. If you have questions on any of this, of course, we'll meet during our normal time. But you can also email me or Google Chat, and we can figure out how to get you through this. But I hope you guys have a great day, and I'll see you soon.